Surface tension is the elastic tendency of the fluid surface which makes it acquire the least surface area possible. Surface tension allows insects, usually denser than water, to float and stride on a water surface. At liquid-air interfaces, surface tension results from the greater attraction of liquid molecules to each other than to the molecules in the air. The net effect is an inward force at its surface that causes the liquid to behave as if its surface were covered with a stretched elastic membrane. Thus, the surface becomes under tension from the imbalanced forces, which is probably where the term surface tension came from, because of the relatively high attraction of water molecules for each other. Water has a higher surface tension compared to that of most other liquids. Surface tension is an important factor in the phenomenon of capillarity. Surface tension has the dimension of force per unit length, or of energy per unit area. The two are equivalent, but when referring to energy per unit of area, it is common to use the term surface energy, which is a more general term in the sense that it applies also to solids. In materials science, surface tension is used for either surface stress or surface free energy. Causes. The cohesive forces among liquid molecules are responsible for the phenomenon of surface tension. In the bulk of the liquid, each molecule is pulled equally in every direction by neighboring liquid molecules, resulting in a net force of zero. The molecules at the surface do not have the same molecules on all sides of them and therefore are pulled inwards. This creates some internal pressure and forces liquid surfaces to contract to the minimal area. Surface tension is responsible for the shape of liquid droplets. Although easily deformed, droplets of water tend to be pulled into a spherical shape by the imbalancing cohesive forces of the surface layer. In the absence of other forces, including gravity, drops of virtually all liquids would be approximately spherical. The spherical shape minimizes the necessary wall tension of the surface layer according to Laplace's law. Another way to view surface tension is in terms of energy. A molecule in contact with a neighbor is in a lower state of energy than if it were alone. The interior molecules have as many neighbors as they can possibly have, but the boundary molecules are missing neighbors and therefore have a higher energy. For the liquid to minimize its energy state, the number of higher energy boundary molecules must be minimized. The minimized quantity of boundary molecules results in a minimal surface area. As a result of surface area minimization, a surface will assume the smoothest shape it can. Since any curvature in the surface shape results in greater area, a higher energy will also result. Consequently, the surface will push back against any curvature in much the same way as a ball pushed uphill will push back to minimize its gravitational potential. Energy. Effects of surface tension. Water. Several effects of surface tension can be seen with ordinary water. A. Beading of rainwater on a waxy surface, such as a leaf. Water adheres weakly to wax and strongly to itself, so water clusters into drops. Surface tension gives them their near spherical shape, because a sphere has the smallest possible surface area to volume ratio. B. Formation of drops occurs when a mass of liquid is stretched. The animation shows water adhering to the faucet gaining mass until it is stretched to a point where the surface tension can no longer keep the drop linked to the faucet. It then separates and surface tension forms the drop into a sphere. If a stream of water was running from the faucet, the stream would break up into drops during its fall. Gravity stretches the stream, then surface tension pinches it into spheres. C. Flotation of objects denser than water occurs when the object is non-wettable and its weight is small enough to be borne by the forces arising from surface tension. For example, water sliders use surface tension to walk on the surface of a pond. The surface of the water behaves like an elastic film. The insect's feet cause indentations in the water's surface, increasing its surface area. D. Separation of oil and water is caused by a tension in the surface between dissimilar liquids. This type of surface tension is called interface tension, but its chemistry is the same. Tears of wine is the formation of drops and rivulets on the side of a glass containing an alcoholic beverage. Its cause is a complex interaction between the differing surface tensions of water and ethanol. It is induced by a combination of surface tension, modification of water by ethanol together with ethanol evaporating faster than water. A. Water beading on a leaf. B. Water dripping from a tap. C. Water does stay atop the liquid because of surface tension. D. Lava lamp with interaction between dissimilar liquids, water and liquid wax. E. Photo showing the tears of wine phenomenon. Surfactant surface tension is visible in other common phenomena, especially when surfactants are used to decrease it. Soap bubbles have very large surface areas with very little mass. Bubbles in pure water are unstable. The addition of surfactants, however, can have a stabilizing effect on the bubbles. Notice that surfactants actually reduce the surface tension of water by a factor of 3 or more. Emulsions are a type of solution in which surface tension plays a role. Tiny fragments of oil suspended in pure water will spontaneously assemble themselves into much larger masses. But the presence of a surfactant provides a decrease in surface tension, which permits stability of minute droplets of oil in the bulk of water. Physics. Physical units surface tension, usually represented by the symbol gamma, is measured in force per unit length. Its SI unit is Newton per meter, but the CGS unit of dyne per centimeter is also used. Surface area growth. The surface tension may be defined in terms of force or energy. In terms of force, surface tension of a liquid is the force per unit length. In the illustration on the right, the rectangular frame, composed of 3 unmovable sides that form a U shape, and a 4th movable side that can slide to the right. Surface tension will pull the blue bar to the left. The force required to hold a the movable side is proportional to the length of the movable side. Thus the ratio depends only on the intrinsic properties of the liquid, not on its geometry. For example, if the frame had a more complicated shape, the ratio, with the length of the movable side and the force required to stop it from sliding, is found to be the same for all shapes. We therefore define the surface tension as. The reason for is that the film has 2 sides, each of which contributes equally to the force, so the force contributed by a single side is. In terms of energy, surface tension of a liquid is the ratio of 1, the change in the energy of the liquid, and 2, the change in the surface area of the liquid. This can be easily related to the previous definition in terms of force. If is the force required to stop the side from starting to slide, then this is also the force that would keep the side in the state of sliding at a constant speed. But if the side is moving, then the surface area of the stretched liquid is increasing while the applied force is doing work on the liquid. This means that increasing the surface area increases the energy of the film. The work done by the force in moving the side by distance is, at the same time, the total area of the film increases by. Thus, multiplying both the numerator and the denominator of by, we get. This work is, by the usual arguments, interpreted as being stored as potential energy. Consequently, surface tension can be also measured in SI system as joules per square meter and in the CGS system as ergs per square centimeter. Since mechanical systems try to find a state of minimum potential energy, a free droplet of liquid naturally assumes a spherical shape, which has the minimum surface area for a given volume. The equivalence of measurement of energy per unit area to force per unit length can be proven by dimensional analysis. Surface curvature and pressure. If no force acts normal to a tensioned surface, the surface must remain flat. But if the pressure on one side of the surface differs from pressure on the other side, the pressure difference times surface area results in a normal force. In order for the surface tension forces to cancel the force due to pressure, the surface must be curved. The diagram shows how surface curvature of a tiny patch of surface leads to a net component of surface tension forces acting normal to the center of the patch. When all the forces are balanced, the resulting equation is known as the Young-Laplace equation, where delta P is the pressure difference, known as the Laplace pressure, is surface tension. Rx and y are radii of curvature in each of the axes that are parallel to the surface. The quantity in parentheses on the right-hand side is in fact the mean curvature of the surface. Solutions to this equation determine the shape of water drops, puddles, muesli, soap bubbles, and all other shapes determined by surface tension. The table below shows how the internal pressure of a water droplet increases with decreasing radius. For not very small drops the effect is subtle, but the pressure difference becomes enormous when the drop sizes approach the molecular size. Floating objects. When an object is placed on a liquid, its weight Fw depresses the surface, and is balanced by the surface tension forces on either side Fs, which are each parallel to the water's surface at the points where it contacts the object. Notice that the horizontal components of the two F's arrows point in opposite directions, so they cancel each other. But the vertical components point in the same direction and therefore add up to balance Fw. The object's surface must not be wettable for this to happen, and its weight must be low enough for the surface tension to support it. Liquid surface. To find the shape of the minimal surface bounded by some arbitrary shaped frame using strictly mathematical means can be a daunting task. Yet by fashioning the frame out of wire and dipping it in soap solution, a locally minimal surface will appear in the resulting soap film within seconds. The reason for this is that the pressure difference across a fluid interface is proportional to the mean curvature, as seen in the Young-Laplace equation. For an open soap film, the pressure difference is zero, hence the mean curvature is zero, and minimal surfaces have the property of zero mean curvature. Contact angles. The surface of any liquid is an interface between that liquid and some other medium. The top surface of a pond, for example, is an interface between the pond water and the air. Surface tension, then, is not a property of the liquid alone, but a property of the liquid's interface with another medium. If a liquid is in a container, then besides the liquid-air interface at its top surface, there is also an interface between the liquid and the walls of the container. The surface tension between the liquid and air is usually different its surface tension with the walls of a container, and where the two surfaces meet, their geometry must be such that all forces balance. Where the two surfaces meet, they form a contact angle, which is the angle the tangent to the surface makes with the solid surface. The diagram to the right shows two examples. Tension forces are shown for the liquid-air interface, the liquid-solid interface, and the solid-air interface. The example on the left is where the difference between the liquid-solid and solid-air surface tension is less than the liquid-air surface tension, but is nevertheless positive, that is in the diagram. Both the vertical and horizontal forces must cancel exactly at the contact point, known as equilibrium. The horizontal component of is cancelled by the adhesive force. The more telling balance of forces, though, is in the vertical direction. The vertical component of must exactly cancel the force. Since the forces are in direct proportion to their respective surface tensions, we also have, whereas the liquid-solid surface tension is the liquid-air surface tension, is the solid-air surface tension, is the contact angle, where a concave meniscus has contact angle less than 90 degrees and a convex meniscus has contact angle of greater than 90 degrees. This means that although the difference between the liquid-solid and solid-air surface tension is difficult to measure directly, it can be inferred from the liquid-air surface tension and the equilibrium contact angle, which is a function of the easily measurable advancing and receding contact angles. This same relationship exists in the diagram on the right. But in this case we see that, because the contact angle is less than 90 degrees, the liquid-solid air surface tension difference must be negative. Special contact angles observe that in the special case of a water-silver interface where the contact angle is equal to 90 degrees, the liquid-solid air surface tension difference is exactly zero. Another special case is where the contact angle is exactly 180 degrees. Water with specially prepared Teflon approaches this contact angle of 180 degrees occurs when the liquid-solid surface tension is exactly equal to the liquid air surface tension. Methods of measurement. Because surface tension manifests itself in various effects, it offers a number of paths to its measurement. Which method is optimal depends upon the nature of the liquid being measured, the conditions under which its tension is to be measured, and the stability of its surface when it is deformed. Do no eye-ring method. The traditional method used to measure surface or interfacial tension. Wetting properties of the surface or interface have little influence on this measuring technique. Maximum pull exerted on the ring by the surface is measured. Do no eye pad method. A minimized version of do no eye method uses a small diameter metal needle instead of a ring, in combination with a high sensitivity microbalance to record maximum pull. The advantage of this method is that very small sample volumes can be measured with very high precision, without the need to correct for buoyancy. Further, the measurement can be performed very quickly, minimally in about 20 seconds. First commercial multi-channel tensiometers (CMCA) were recently built based on this principle. Wilhelm plate method. A universal method especially suited to check surface tension over long time intervals. A vertical plate of known perimeter is attached to a balance, and the force due to wetting is measured. Spinning drop method. This technique is ideal for measuring low interfacial tensions. The diameter of a drop within a heavy phase is measured while both are rotated. Pendant drop method. Surface and interfacial tension can be measured by this technique, even at elevated temperatures and pressures. Geometry of a drop is analyzed optically. For details, see drop. Bubble pressure method. A measurement technique for determining surface tension at short surface ages. Maximum pressure of each bubble is measured. Drop volume method. A method for determining interfacial tension as a function of interface age. Liquid of one density is pumped into a second liquid of a different density and time between drops produced is measured. Capillary rise method. The end of a capillary is immersed into the solution. The height at which the solution reaches inside the capillary is related to the surface tension by the equation discussed below. Stalagmometric method. A method of weighting and reading a drop of liquid. Sessile drop method. A method for determining surface tension and density by placing a drop on a substrate and measuring the contact angle. Vibrational frequency of levitated drops. The natural frequency of vibrational oscillations of magnetically levitated drops has been used to measure the surface tension of superfluid 4He. This value is estimated to be 0.375 dyn per centimeter at T equals 0 K. Resonant oscillations of spherical and hemispherical liquid drop. The technique is based on measuring the resonant frequency of spherical and hemispherical pendant droplets driven in oscillations by a modulated electric field. The surface tension and viscosity can be evaluated from the obtained resonant curves.